Right, good day to everyone. This is a lecture about the applications of geophysics. I am Rico de la Peña, and the purpose of this lecture is to help you familiarize with the applications of different geophysical methods. And we will be talking about petroleum exploration, mining exploration, and civil and environmental engineering applications. Right? Now, there are three important elements to discuss in petroleum exploration. One is the geological controls, second is the sedimentary basin, and third is the geophysical exploration method. Now, geological controls, so what are they? These are the processes which are required to have exploitable oil and gas. So all these processes should be present or should have occurred in your area in order to have significant quantities of oil and gas, right? And yeah, geological controls, of course, are the elements of your petroleum system, and they affect the occurrence of oil and gas. So I'll just discuss them later, so you won't, just to clarify things up. Now, these are the processes which are involved in the generation of oil and gas. The first step is the generation of oil or gas from your source rock, and these involves heating up an organic rich rock such as shale. Once the oil or gas is generated or extracted from your source rock, naturally extracted, the next step or what should happen here is the oil and gas should migrate, all right, upwards and accumulate and undergo accumulation, and they also should stay in place by means of a gas or an oil cap. Right, so let's discuss them one by one. The elements of a petroleum system. Yeah, the source rock is where your oil or gas comes from, and then your reservoir rock is where they accumulate, and then trap is a geologic structure. Okay, it could be a structural configuration or stratigraphic or a combination of both. And what's important about a trap is impermeability or low permeability. So a trap, the role of a trap is to hold or and catch migrating oil and gas and confine them laterally and vertically. Now we also have a seal, which might be similar or just part of your trap, but the seal is the part or is a cap rock which prevents oil and gas from leaking out. All right. Another element is the migration or the movement of oil and gas from the source rock to reservoir rock. Now, this is an example of a source rock from England. You can see here a dark colored rock, which is indicative of organic content. And this is a close up of a source rock sample. You can see here oil and alternating oil prone and low potential rock. Now, your oil prone rocks typically have a total organic content of more than 2% by weight organics, and they typically have a high hydrogen index, as you can see here, right? Now, we also have our reservoir rock, which is basically just a storage of your migrating oil and gas. The key feature of a reservoir rock is porosity and permeability. Porosity is just the amount of void space, right, that is made available through fractures or through the natural porosity of your rock, such as in sandstones. And then permeability is important, particularly with respect to the connection of, or rather hydraulic connection of your reservoir rock to the source rock. So they have to be hydraulically connected, meaning fluids can transmit from the source rock to the reservoir rock. Otherwise, you won't have any accumulation. Now, this is an example of a reservoir rock from Texas, USA. This is a serpentinite reservoir, right? And naturally, serpentinite typically doesn't have a primary porosity or permeability, but due to alteration and fracturing, right, it has secondary permeability and porosity. Okay, so reservoir rock is not limited to sedimentary rocks. It could be any type of rock. Now let's talk about traps. Traps are, as said before, they aid in the accumulation. Hello. They aid in the accumulation and confinement of your oil and gas. We have different types of traps here. First, on your left is an anticline. What an anticline does is it is basically shaped like a dome or a sort of a 3D dome feature. And if part of the anticline is a low permeability formation like shale or mudstone, it can definitely provide a permeability barrier here to prevent your oil or gas from migrating out of your anticlinal trap. Another type of trap is a pinch out trap, or a which is caused by a facies change or depositional environment change, right? As we can see here, we have a facies change here from something like shale into sandstone, right? And this part is hyperpermeability, high porosity, but due to the facies change, it is bounded by shale and limestone, which are relatively impermeable. So they are trapped in this pinch out configuration. Another type is an unconformity. As you can see here, we have here a sandstone formation, which is naturally porous and permeable, so it's not a good trap. But due to unconformity or erosional change, we have here an overlying impermeable shale formation. Now, the last two types are structural type of traps. This one is a fault type of trap. As we can see here, sorry, we have a sandstone here, and then we have a fault. Now, note that not all faults are impervious. It depends on the infill material of the fault. It could be highly permeable, and it could be also highly permeable. So in this case, the fault, I think it has infill of fine materials like clay, so it is a it is actually trapping the oil and gas in here. The last type is a salt dome. Now, salt dome is essentially it's like an intrusive igneous rock. except that it involves a mass of salt, right? Salt has a very, very low density, and it can actually rise from the bottom. Due to density, it can actually intrude into your overlying rocks, and it can form a structure that looks like an anticline. Now let's move on to the seal or the cap rock, right? Seal is basically the role of your cap rock is to just hold down your accumulated oil and gas. As we can see here in the figure, we have here a formation that consists of sandstone and shale, which are your reservoir rock. And then we have here actually here in the topmost portion is an upper Cretaceous shale, which is acting as your cap rock. So this upper part here is sealing. It is relatively impervious, so it is sealing down all the oil and gas below. Now let's talk about sedimentary basins, right? Sedimentary basins have an important role in petroleum exploration because they are where you are most likely to find all these uh, geological controls that are conducive for the formation, generation, migration, and accumulation of oil and gas. Okay, so this is the only geological setting where you have a large likelihood of finding oil and gas, right? And there are sedimentary basins in divergent tectonic boundaries, and there are also sedimentary basins in convergent tectonic boundaries. Right, just an overview. This is an example of a sedimentary basin in Saudi Arabia and Qatar. And those two nations are well known for their vast oil reserves. And we can see here that this sedimentary basin is a huge one. It is minimum 8 kilometers 8 kilometers deep. Now note that the minimum depth for sedimentary basins in order for them to generate oil and gas is 3 kilometers. Okay, while here you have more than 8 kilometers, 8 kilometer deep sedimentary basin, right? Okay, right. Now let's talk about sedimentary basins and divergent tectonic boundaries. Of course, sedimentary basins, in order to have a basin, the first thing you need is a large area undergoing subsidence, and divergent boundaries are one of your candidates or one of your areas where it is conducive for sedimentary basins to form because you are having seafloor spreading, which is which involves large scale subsidence of your oceanic floor. Now let's talk about sedimentary basins in a convergent tectonic boundary. This is an illustration of a tectonic boundary, right, involving subduction. And what we can see here is, or what we should note here is, we are actually destroying, right? We are destroying plates here, and over time we are actually losing. We are actually losing some some land mass in here, and the implication of that is it's actually very difficult to have old set and deep sedimentary basins in a convergent tectonic boundary, unlike in divergent ones, because in a divergent tectonic boundary you just have a subsiding area that is just expanding and expanding over time. In a convergent tectonic boundary, you are just destroying your your crust over time, and it is very difficult to find very old sedimentary basins in this area. So there's a smaller likelihood of finding oil and gas in convergent tectonic boundaries. Another added factor is your partial melting, which results in rising of magma, which increases the heat. Okay, too much heat can turn your petroleum into gas, and okay, so most of the time you can expect just gas in convergent boundaries. Now let's proceed to the geophysical methods and their targets in the context of petroleum exploration. Right? Gravity methods. Now note that gravity is all about density. Gravity can detect low density and high density objects, and gravity can also detect presence and absence of objects like voids or hollows. Now, gravity can be used to locate salt domes. As discussed before, salt domes uh, are conducive for creating salt dome traps, which accumulate oil and gas. And also, gravity can be used to locate basement rocks. Now, why are basement rocks important in petroleum exploration? Basement rocks can tell you, especially if you are dealing with a sedimentary basin, the bottom of your sedimentary basin is your basement rock. Now, if you can determine the depth of your basement rock on a sedimentary basin, you can estimate the thickness of your sedimentary rock, which in turn can lead you to estimate or calculate the volume of your oil and gas in that area. But it's a much more complex story here. Another method is your magnetic method. Again, you can use it to estimate the depth of your basement rock in your sedimentary basin. And of course, that can lead you to the thickness of your sedimentary basin. And the third and the most important is the seismic, particularly seismic reflection. Seismic reflection can provide clues on the stratigraphy, right? So stratigraphy is important as we have discussed previously. All right, so we have to know the rock type so that we can determine if the rock could be a source rock or a reservoir rock. Okay, what is the permeability of that rock, and so on. Seismic can also provide clues on the geologic structures and also the rock properties. Now, this is an example of gravity being used for for locating a basement structure in salt dome. So let's go by this figure. Now look at the left figure. We have on the top left a milligauss is a measure of gravity, or you can imagine milligauss as a relative measure of density, right? and your x-axis is the traverse distance of your gravity survey, and below is the ideal geologic section of what is being surveyed. Now below is a basement structure. Hello. Below is a basement structure, and overlying your basement structure is your sedimentary basin. So you have two sedimentary basins here. And what you can see here in your gravity survey is that while you are over the sedimentary basin area, you are detecting a relatively low gravity or um, low density. Yeah, you're detecting low density here. And as you pass by your basement structure, which is typically more dense rocks like igneous rocks, like mafics, ultramafics, which have a much bigger density than your sedimentary rocks, we are registering here a large gravity reading. All right. Now, the next example here is a salt dome. Okay. And of course, the reverse happens here. Salt has a very low density, like half, I think it's almost half the density of a normal rock. So here, as we are passing by your other types of rocks, you are registering a relatively high gravity reading or a relatively high density. And and as we as we pass by as we pass by the salt dome, we are registering a low gravity or a low density body here. Now, for the magnetic method, this is slightly more complex because we are actually, or rather, in magnetic methods, you also have to account here for the switching of your magnetic polarity. So, if you will go back to your historical geology, note that in a divergent boundary, right? So in a divergent boundary, you have new ocean floor that is being created over time. And note that um, each uh, segment, or every time you create a new portion of an oceanic floor, your newly formed rock will record the magnetism of the Earth at the time of creation. So note that Earth changes its magnetic polarity, I think every 1 million to 500,000 years. So what you can expect on your oceanic floor is you have a banding of you have rocks here that are switching out in terms of magnetic polarity. Here, like shown here, you have black, white, black, white, black, white. Okay, and in consequence, the magnetic anomaly or the magnetic intensity here is actually switching in terms of it's going from positive to negative, positive to negative, positive to negative. Okay, but what's actually important here when you are looking for uh, or when you're looking for the basement, or when you're looking for a sedimentary basin, is that as you pass by an area with a lot of magnetic rocks, like here, so in this part you have a shallow basement. So the basement here is just near the ground surface. So when you are just near your basement rocks, you can register a high amplitude of magnetic intensity reading, regardless of whether it's going positive or negative, as opposed to an area where you are quite far from your magnetic rocks or your magnetic basement rocks, like here. So you have a lot of sedimentary rocks here. So what you get here is a more subdued reading of your total magnetic intensity. Now for seismic is more or less an imaging. You can imagine seismic reflection as a photograph of your subsurface. Actually, it works the same principle as an ultrasound. So you can actually see the outlines of the objects beneath, though they're not always representative of the actual conditions due to different phenomenon, as we will be discussing in the later stages, in the later parts of this course. But what's important here is we can see here different geologic structures, right? So we have some synclinal forms, anticlinal forms. You also have here a normal faulting. You can see here uh, the formation here is sort of collapsing. So this part has moved downward. So you have normal faulting here, right? And there are other structures present in this seismic section. Now there is also an emerging discipline within seismic geophysics, and this is what we call seismic stratigraphy. In seismic stratigraphy, okay, what we do here is we do a step-by-step interpretation. So we start here with an interpreted seismic profile, but note that there are already apparent patterns here, like there are clear layerings here, all right, and there's also a sort of a change or a boundary here which delineates a change in pattern in the sedimentary layerings here. Okay, so we start with the layers in the seismic section, and then we proceed with the uh, facies level interpretation here, so they can interpret here which is the delta, which is the shore face, which is the slope, and then eventually the basin floor. And then further, they can eventually interpret the relevant formations here. This example is from Vietnam, so you have these names like Bien Tong, Nam Con Son. Okay. Now let's proceed with the civil and environmental engineering applications of geophysics. And there actually almost all of the geophysical methods can be used in civil and environmental engineering applications, but this is actually quite misleading because the discipline of civil and environmental engineering itself is a huge and a very diverse field. Unlike previously as discussed in petroleum exploration, we are more or less just looking for one type. We're just looking for one or two types, which is oil and gas, and we are dealing with a more or less one type of geological setting, which is sedimentary basins. Now, in civil and environmental engineering, you are dealing with a lot of stuff here, like you're looking for bombs. One day you're looking for bombs, other day you're looking for pipelines, and then the next day you will be looking for contaminants, And then the other day we'll be looking for, or you're trying to measure or estimate the bearing capacity of your foundation and so on. So it's there's a lot of methods applicable in this field, but note that this field itself has a lot of different problems, which might require different methods. As you can see here, for example, so this is more or less a table showing the applicability of different geophysical methods versus their applications. For example, let's look at your bottom right legend here showing the codes for the applications. So let's say for example you're looking for unexploded ordnance, or basically you're looking for vintage bombs. All right, so UXO, or unexploded ordnance, which is under number 12 here. So column number 12, if you are looking for vintage bombs, so the primary methods for looking for vintage bombs are your magnetic method. You can also use electromagnetic method. Okay. And to a certain degree, you can also use GPR, but this is just a secondary method compared to EM and magnetics. Okay. So for UXO, you only have more or less two main geophysical methods that you can use. Okay. So as you can see here, each application will require specific methods. Okay. So just because I said previously that you can use almost all of the geophysical methods in civil environmental engineering, it doesn't mean that is one method you can just it doesn't mean that you can just pick up say for example electromagnetic method and expect it to use it in uh, all types of your problems. Okay. But if you're looking here for a more or less a versatile equipment, you can see here that electromagnetic is more or less applicable to most engineering problems. Also resistivity. Okay. All right. Although in reality, in my experience, especially as I'm working mostly with geotechnical and engineering geological problems, I'd say the most important method here is your seismic refraction and seismic MASW, which I will be talking about later in this course. Okay, so bottom line, don't this chart is a good starting point, but you have to research in detail your problem and the method that you are considering to use. So in the next slides, I'll be just showing just an overview of different uses of, or an overview of the different applications of geophysics in engineering. But this is not a comprehensive discussion, all right? Now, let's look at gravity. Gravity, as discussed previously, can detect low density objects. And for this example, we actually have a cavity or a cave. And of course, cave contains air, or if you are dealing with a wet season, a cave might contain just water. So water or air has a low density, and when you're doing a gravity survey, you can expect a cave to register a low gravity reading here. So in here, we are registering here a negative. gravity reading, a highly negative gravity reading. So this means, so it doesn't mean that your object here has a negative gravity. It only means that you have a relatively low gravity reading here. Okay. Another example of use of gravity in engineering is the use of microgravity surveys for detecting, all right, stress release induced fracturing of rocks around a around the tunnel section. So this is a tunnel, and they were, and note that when you are making a tunnel underground, of course all tunnels are underground. When you have a tunnel, what happens is you remove here parts of rock. So you are removing some support here. And what happens is when you are underground, there is a lot of stress. Okay. You have like kilometers of overburden here that is squeezing out your rock. Now, if you remove a portion of rock here, when you do a tunnel, what happens is the rock here wants to squeeze out into the tunnel. So they want to exit, they want to relax a little bit. So they want okay. So what happens here is when you have a void or a tunnel here, um, parts of the surrounding rock will sort of undergo fracturing. Okay, they undergo like relaxation. Uh they sort of expand. They undergo expansion and they can fracture. Okay, so fracturing result can be detected by microgravity in form of lowering of their gravity reading, because when rocks fracture, they undergo loss in density. Okay, and this is another example for volcano monitoring. This is from a study in Mount Etna in Italy. And above the drawing here is a gravity reading measured by this gravity station. Okay, and this is a gravity reading over time. Okay, so what happened here is that during the eruption, there was a loss. Okay, so you're basically losing magma chamber, some magma here in your magma chamber. So during the eruption, there was a loss in density within the volcano because the magma chamber lost some magma. And then after the eruption, there was an accumulation of foam. Okay, so after the eruption, the density of your magma chamber bounced back to its normal levels. Okay, but after that, there was also an accumulation of volatiles or foams, which again lowered the density of your volcano or the magma chamber. Now for magnetics, this is an example of using magnetic methods for locating subsurface utilities. By utilities, I am referring to pipelines, water pipelines, electrical lines. What else? Yeah, mostly electrical and water lines. And right. And this is a 2D section of a magnetic. Sorry. And this is a 2D section of the magnetic reading in the subsurface. Okay. So in here they were looking for metal pipes. Okay. And these are the known locations of the metal pipes. And you can see here a contour. All right. So what they did here is they did a magnetic survey and then they did some inversion modeling, which we will discuss later. But inversion modeling is basically in geophysics, what we normally measure is just a response or just a total response of the ground, okay, depending on the geophysical method that you use. So you always start with the total response. So a good analogy here is that, for example, you have a group of five friends who is shouting, who is just shouting. So you can hear their voices. Okay, so that you know that they are your group of friends and they are shouting, but you might not immediately know. Uh, Sorry. Let's say, for example, you have a group of friends who are shouting and they're shouting different words at the same time. So each friend is shouting a different word, and so on the outset, you may know that you are hearing your group of friends shouting. So they're shouting, but you don't know what are they saying individually. Okay, so that's how J-physics works. You just know that your group of friends are shouting, but you don't immediately know what each what what word is each friend shouting. Okay, so you can do some guesswork here. Okay, so we can do some guesswork like record their voice and play back over and over and try to guess. Okay, which person is shouting which word. So that's how inversion works in geophysics. Okay, so you're doing some intelligent guess. You're trying to deaggregate or separate uh, your tot. You're starting with a total response and you're trying to break it down into smaller pieces. Anyway, that's for later discussion. All right, so this is a 2D model of the magnetic response of the subsurface, and there are known metal pipes. And what we are seeing here is we are registering a large magnetic intensity where the metal pipes are known to be located. Okay. This is another example in a landfill. Okay. And what they did here is they scattered known objects at known locations. Okay, so this is just a calibration study. So they scattered different garbage here, metal garbage, and then they did a contouring, magnetic contouring in the area, and they were able to see how the metallic objects are actually showing up in their magnetic survey. Now, probably one of the most important use of magnetics in civil and environmental engineering is the detection or mapping of unexploded ordnances or UXO. All right, and note that the magnetic intensity reading of a certain object decreases as you go farther away from that object. And this is just a rough guide on how you can determine, okay, on whether your magnetic equipment can detect that UXO. Let's say, for example, your boss assigned you to look for 1,000 pound bombs in a construction site. Okay, So let's say, for example, they were constructing a mall, and then they suspected that since the mall site is a former uh, World War II base, there might be bombs in the area, and they think that there are 1,000 pound bombs in the area. All right, so you're looking for 1,000 pound bombs, and you know that the area has a soil layer that is at least 6 meters deep, or at most 6 meters deep. Okay, so you have a 6 meter deep soil, and you know that the bomb could be anywhere between 0 to 6 meters deep. Okay, so we just trace this line, and then we trace this 6 meters deep, and then project it here to the x-axis, to the y-axis. And from here, we can see that the magnetic field intensity of a 1,000 pound bomb at 6 meters deep is approximately, I'd say approximately, this is 30, around 25 or more, 25 nanoteslas. Okay. Now, if your equipment or your magnetometer can only detect 50 nanoteslas. Okay, so let's say your equipment has a minimum detection rate at 50 nanoteslas. So this is much bigger than your threshold intensity. So not, you won't be able to look, or your equipment won't detect that object. So you might want to look for a more precise equipment. Okay, for example, a magnetometer that can read 20 nanoteslas, or even better, look for an equipment that can read 5 nanoteslas. Okay, because these are sensitive enough. These would be sensitive enough to detect a 25 nanotesla change in magnetic intensity. Okay, so that's how this chart works. Okay, so this tells you whether you can detect a certain object at a certain depth using a certain equipment. Now let's move to resistivity. Resistivity is just a it's just a measure of of resistivity is just an inverse of conductivity. Okay, so the more conductive your material is, the lower the resistivity. And this is an example of using a resistivity survey to map out a landslide. Okay, although note that lands that resistivity relies on the conductivity or the resistivity of materials, and resistivity is greatly affected by presence or absence of water. Okay, and my disclaimer here, as someone who's been working for landslides for almost 10 years, is that not all landslides are, you can't always apply resistivity on landslides. Okay, because resistivity depends so much on groundwater. Okay, and there are so many types of landslides in that you can encounter. So anyway, in this case, the landslide here is controlled by groundwater. So the landslide is being destabilized by high groundwater levels. Okay, and the result is they are registering here as low resistivity areas. Okay, and this is your more or less your landslide here. Okay, another example of resistivity is for construction. So in here, they are using electric potential measurement in order to detect presence of metal rebars within a concrete column. Okay, so it's important for metal rebars to be present in the concrete column because they serve as reinforcement for your structure. And yeah, in here they're using resistivity to see if there's actually a metal rebar. Okay, so you can see here in this example, uh, okay, so it's not quite clear. I'll just skip this figure for now. Okay, now for electromagnetics. Okay, now note that electromagnetics is essentially just reading the conductivity of your material. So it's very similar to resistivity survey. Okay, so don't be confused with electromagnetics. It's what you measure in electromagnetics is totally different from what you measure in magnetics. Okay, electromagnetics is actually much closer to resistivity survey, except that in electromagnetics you are using electromagnetic induction. Okay, which doesn't require a ground contact. Okay. All right. So going back to this figure, this is an exploration map, and they are looking for contaminants, particularly isochloride contaminants. And isochloride is or water that contains isochlorides have an elevated concentrations of ions, and ions have high conductivity or low resistivity. Okay, okay, and in this map, the actual location of the contaminant is shaded in gray. Okay, so this whole gray shade is your contaminant, and then your dark contour here is the measured concentration of your isochlorides. Okay, so the more isochlorides you have, the more conductive the fluids are. All right, and it's quite hard to see 400. And then the other contour here, the dashed line contours here are your resistivity contours derived from electromagnetic surveys. Okay, so what we can see here is okay, so we have here in this portion we have a decreasing in this area. We have relatively low isochloride concentrations in here, so it goes from 55, 50, 45, and then here you have a relatively low isochloride concentration. So when you have low concentration of isochlorides, relatively you have a relatively low conductivity, which equates to relatively high resistivity. Okay, so it is coinciding with this area. So the area with low isochloride concentration is coinciding with an area of high resistivity from the EM survey. Hmm. Another method is the ground penetrating radar, right? And ground penetrating radar is actually closer to seismic reflection in a sense that it images the subsurface And you can actually see the patterns or the outlines of the objects beneath. Okay, although the main difference between GPR or ground penetrating radar and seismic reflection is that they rely on different material properties. Okay, in ground penetrating radar, you are relying on the electrical properties of the subsurface, while in the seismic reflection, you are relying on the stiffness of your materials. Right? So the boundary of the water table is okay. So as discussed before, water affects the electrical properties of your soil and rock. So when you have a water table, you can expect a sharp change in electrical property of your materials. So a wet soil and a dry soil will have highly contrasting electrical properties or electrical readings, and that's the and when you're using GPR, when you encounter a sudden change in electrical properties, you get a strong reflection or you get a strong outline here. Right? So that's how you can more or less map out water table using GPR. Okay, although GPR is actually quite difficult to interpret because it is quite subjective, and there are a lot of objects that can produce this kind of signature. Right? Now let's talk about seismic reflection, which is basically just an image of the outline of the objects in the subsurface. Right? And this figure is showing a seismic reflection for a bedrock valley that contains clay and sand deposits. Okay, so as discussed previously, seismic reflection can detect changes in stiffness. Okay, so if you're gonna go back to your soil or rock mechanics class, stiffness is it's a measure of how brittle your material is. Okay, the more brittle your material is, the higher the stiffness. Uh, okay, so sand, for example, is definitely more stiff compared to clay. Okay, and what we are seeing here is every time there is a change in stiffness or change in brittleness of your subsurface materials, you get a reflection or you register some outlines here. All right, so this part is silt and clay, this part. So then you have a change in stiffness, so you have a layer boundary, and this is sand, and so on. Although typically seismic reflection and other geophysical readings are best calibrated with an actual drilling. Okay, 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 because most of the time these layers are quite ambiguous, and it's always best to have a drilling done side by side with geophysics, so we can verify or confirm your interpretations. Now, this is another example of using seismic reflection, this time for an active fault, right? So what we have here is basically you have here two layers. So this is one formation. This lightly shaded one is one formation. This dark one is another formation. Okay, so what they saw here is they think this layer here uh, was offset. Okay, so this layer here is suddenly terminated and somewhat continued on this side. And they think that this termination of the layer was caused by a fault which offset this part upward. Okay, so you more or less have here a reverse fault. Okay, so this part was thrusted upward, and then for seismic refraction, all right. So seismic refraction is quite different from seismic deflection. Seismic refraction, what happens here is seismic refraction is not good at detecting the details of the subsurface, but it is good at getting an engineering measurement of the layers in the subsurface. And we will be discussing that later in this course. But for now, just accept that seismic refraction is good for measuring engineering properties, while seismic deflection is good for imaging the patterns of the subsurface. All right, seismic refraction, what you get here is the primary output you get in seismic refraction is the primary pri- uh, is the primary wave velocity or the VP. And primary wave velocity is correlatable with properties of rock or soil that are related to density. Okay, and one of those is the rock quality, is the quality of rock. Okay, so what we can see here is the higher the quality of your rock, okay, the higher the velocity of your seismic of your rock material. So note that when you have a stiff material or a stiff rock, the stiffer your material is, or in some cases the harder your material is, the more efficient and faster they are in when it comes to transmitting seismic waves. So it means that when they are efficient or they respond fast to seismic waves, you can expect them to have higher they allow seismic waves to travel faster. Okay, the best experiment here is to when you are swimming, okay, when you are swimming and you are submerged in a swimming pool and a piece of coin drops in the other end of your swimming pool, okay? So it doesn't matter even if the swimming pool is Olympic size or a small pool, okay? So when a coin drops and hits the floor of the swimming pool at the other side, you can more or less instantly hear the coin dropping. And the reason here is that water has a high water has a high seismic velocity compared to air. Okay? The seismic velocity in air is approximately 300 meters per second, while the seismic while the velo- while the seismic velocity in water is approximately 1000 meters per second. 1000 to 1500. I can't remember the exact number. But anyway, seismic acoustic wave or sound wave, okay? Or rather, seismic wave is just a type of acoustic wave or sound wave. So more or less, when a coin drops at one end of the swimming pool, it produces an acoustic wave or something similar to a seismic wave. And the fact that water allows for faster seismic or acoustic velocity, so it allows you to hear the dropping of the coin faster. And there's also a lot less loss in the sound. compared to when you are in the surface. Okay. Now, another method here is radiometrics or methods which utilize radiation. Okay, so radiation is all about your isotopes, okay, which undergo radioactive decay. And this example is okay. The story here is in the U.S. So they had a lot of radioactive materials due to their arms race with the Soviet Union in the Cold War era. So they had so much nuclear material, and they ended up dumping nuclear material or nuclear wastes in an island in San Francisco, USA. So this area is the Farallon Islands, and they dumped barrels and barrels of nuclear wastes. Okay, and then later on, they somewhat detected an increase in radioactive readings in the area. So what they did is they did an aerial survey of the area. So they had a sort of a scanner which detects radioactivity. Okay, and what they found out is that they think here. So what the data shows here is that there are areas with high radioactivity near the near waste barrels and some of their suspected barrels that were leaking. Okay, but as you can see here, it's not so conclusive because they have barrels here that are suspected to be leaking. Here, shaded dark, and the lighter shaded barrels here are just waste barrels that they think are not leaking. And then when they overlay the radioactive reading here, okay, so areas with high radioactivity here, sorry, this is supposed to be a color scale, but the stupid textbook publishers turned it into grayscale. So it's almost impossible to see which ones have high radioactivity and which ones are have low radioactivity. But as per the book description, what you're supposed to see here is that the areas with high radioactivity are not necessarily coinciding with their barrels that are suspected to be leaking out. So eventually they concluded that the radioactivity was just not abnormal. Okay, so I don't know if they're hiding something, but that's their conclusion in the as written in the textbook. All right. So the purpose of the survey here is to check whether whether barrels that were suspected to be leaking are actually leaking. And what they are supposed to see here is that the supposedly weak leaking barrels are supposed to register high radioactivity. Okay, but that's not what they found. Now let's move on to my favorite subject, which is mineral exploration. Okay, so to be honest, back in my undergraduate days, I almost failed this subject. Okay, so I think a lot. Many of you also love mineral exploration. Okay, so let's discuss briefly what mineral exploration is. Alright, so the gist in mineral exploration is that most of the easy mineral deposits have already been explored and mined. So meaning the gold, the new gold deposits, the new copper deposits that you'll be looking for are so expect to have a lot of difficulty looking for easy deposits because most of them have already been mined and explored. So therefore, the strategy that is, or the meta here, to speak your language, or the meta is to use a staged exploration so as to not waste time and effort looking for minerals. Okay? And to further aid mineral exploration, we have here mineral deposit patterns. Okay, so those are your mineral ore model deposits like your VMS deposits, your porphyry copper deposits. So these are just generalizations or models on how deposits may look like, and they aid us uh, in finding or having a framework of how the minerals would look like, okay, or how they might be distributed in the real world. Okay, so the exploration techniques. Now let's talk about the different exploration techniques. You have remote sensing, which is your satellite imagery, your drone aerial surveys, and so on. They are here to help you get a big picture of your area. Okay, so they are cost effective, especially for the early stages of your exploration. And then the next are your geologic techniques, like your geologic mapping, structural mapping, geomorphologic mapping, and they have different applications depending on what mineral are you looking for. For example, if you're looking for if you're mapping hydrothermal alterations, that's useful for gold exploration. And then structural mapping is useful for everything. And then geomorphologic mapping is useful for deposits which are the which are more or less in the surface, like nickel laterites, placer deposits, and so on. And then you also have your geophysical techniques, okay, which allow you to have a view of the subsurface. Okay, and typically this involves magnetics, gravity, and electromagnetics. And then you also have geochemistry to help quantify the minerals that are present in your exploration area. Okay, so this is how the stages of exploration go. So we start with reconnaissance, which involves areas of hundreds to thousands of kilometers. And then you go to detailed survey, which involve pitting, trenching, geophysics, geochemistry. And then further, you start drilling. Okay. So normally drilling always comes after geophysics. And the reason here is that drilling is always expensive. Okay, drilling is expensive. This is applicable in all aspects of geology, whether you're dealing with mining or petroleum exploration or even in engineering. Okay, drilling is almost always the most expensive part, and it's always preceded by geophysics because geophysics is cheap, it's fast, and it covers a large area. So after your drilling, you proceed with further drilling, which is outline drilling, to further delineate the extent of your ore deposits. and then you go further with drilling to determine the grade of your ores, and then you proceed with the feasibility study to determine if you're gonna proceed with the mine development or not. Okay, so let's proceed with the mineral deposits. You have the terminologies and the types of mineralizations. Okay, for terms, ore is a deposit that can be mined for a profit. So it always depends on the concentration. Okay, so a gold with very very low concentrations might not be considered an ore, or sorry, rather a rock that contains some gold with very very low concentrations of gold might not be considered an ore. And then hydrothermal is anything that is formed in association with hot water or magma heated water. And then sedimentary deposits are ones that are precipitated from solution. So sedimentary deposits are chemically, more or less chemically precipitated, like deposits from lakes, seas, or rivers. While placer are mechanically deposited deposits, particularly by rivers. And then residuals are deposits that are actually weathered and accumulated in place, such as in the case of laterites, which are typically just formed in place. Hello. Hello. Okay, let's proceed. Now, these are the different mineralization types, and let's discuss them one by one. First is the volcanic massive sulfide deposits. All right, so these are deposits that are typically located. Okay, so these are deposits that are typically located in remains of volcanic edifices. Okay, and sorry, correction. Volcanic massive sulfides are associated with hydrothermal vents. Okay, in submarine areas, and these hydrothermal vents are rich in sulfides. And the best indicate and one of the popular indicators of VMS is the black smoker complex, which will I'll be showing you later on. But these are VMS contain sulfides, and they have different deposits like your iron oxides in form of banded iron formations. Okay, you also have iron massive sulfides in the uh, outer perimeter of your VMS. And then further inside, you have your zinc lead massive sulfides. And then closer to the vent, you have your copper massive sulfides. And then below is your copper footwall. Okay. And this is the black smoker that I was talking about. Okay, so this is a hydrothermal vent which is just issuing a black cloud that is full of sulfides. Okay, and these sulfides deposit in the surrounding areas of the VMS, and they eventually build up your deposits. Now, for geophysical methods, now for geophysical methods, there are various methods that can be used for VMS exploration depending on your target. If you're looking for copper, lead, and zinc, okay, you can use electromagnetics because they are highly conductive. Now, for general exploration, Massive sulfides, okay, by their nature they involve heavy minerals, so they actually have a relatively high density compared to their surrounding rock, and you can use gravity. And then another important associated mineral is pyrrhotite, which is one of the minerals with really high magnetic intensity, and you can use magnetics to look for the associated mineral, which is pyrrhotite. Now for porphyry copper, here the story is you start with an intrusive body, and then you have your hydrothermal fluids which just circulate around and alter the surrounding areas. Now the intrusive body and the area immediate it is your porphyry copper deposit, and then the area above it, okay, which is mostly in contact with the hot and acidic hydrothermal fluids, you get your high sulfidation silver and copper, sorry, gold and copper. And then further away from your porphyry copper, you have hydrothermal fluids that are more or less cool and relatively low in sulfides. You get your copper and silver deposits, or your low sulfidation copper silver deposits. Okay, and this is a typical or rather this is the model for porphyry copper deposits. You have different zones of alterations. You have potassic, which contains potassium, which has a geophysical significance, and then you have your philic alteration, which contains pyrite, and then you have your polylytic alteration, which contains different types of clay. Now, for geophysical methods, porphyry copper, okay, note that uh, certain alteration zones, particularly felsic porphyry alterations, contain magnetite. Okay, while on the other hand, so felsic porphyry copper contains magnetite, so it can have a strong magnetic signature. On the Although on the other hand, propylitic and philic alterations, okay, involve destruction of your magnetite. So these zones, on the other hand, have low magnetic intensity. And then another method that you can use is, of course, your alterations contain potassic alteration, and potassium is one of the most radioactive elements, and they can have radiometric or radioactive signatures. Now let's go to the epithermal gold, or your low sulfidation gold. Hello. All right. Low sulfidation gold is epithermal gold with in low sulfidation area is when your acidic fluids are able to travel far. So they involve low temperatures, and most of the sulfides have deposited elsewhere. And your expected deposits here are gold and silver. Okay, so as before, it involves different clay alterations like propylatic alterations, which contain, and you also have your kaolinite and alunite. You also have cerussite, silica adularia. All right, so as with porphyry copper, you have different. potassic clays and potassic minerals, which can have radioactive signatures. So we can use radiometric methods. And epithermal gold also involves concentration of high density minerals, and they can, as a result, have relatively high gravity uh, anomalies. Now let's move to your high sulfidation, epithermal copper silver. So these involve high temperatures and high sulfide alterations. Okay, so you can expect here arsenic, copper, stibbium, bismuth, tellurium, tin, molybdenum, and sulfur. In terms of geophysics, okay, these are mostly metals. So you can expect high conductivity, therefore low resistivity. And we also have what we call chargeability, which is especially high when you have metals that are dispersed. Okay, so chargeability is a function of presence of metals, fluids, and large surface area. And then also note that the alteration destroys your magnetites in their deposits, so you can expect a low magnetic reading here compared to your host rocks. Okay, so that's what I discussed previously. Then let's proceed with your nickel laterite deposits. Okay, nickel laterite is essentially just mafic or ultramafic rocks which have decomposed in situ. Okay, the best examples here is your laterite deposits in Zambales or in Surigao. And this is your typical laterite profile. Okay, so you start with from the bottom, you have your bedrock, and then further above, you have your serpentinite and your altered bedrock, and then it transitions to your laterite deposits. Okay, so note that in laterites, you have intense leaching of your original parent rocks. Okay, as a result, the intense leaching destroys your magnetites in your parent rocks. So your nickel laterite deposits relatively can show up as magnetic lows or relatively low magnetic intensities compared to your unaltered host rocks. And then if for a more general stage of exploration, okay, when you're looking for nickel laterite, you're more or less looking for ultramafics and your mafic host rocks. So you can start off with gravity to look for your mafic and ultramafic host rocks as they have a high density. Hello, 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 hello. All right, sorry. I was I ended up not recording the last part, so let me repeat this part. So for nickel laterite deposits, for the for the general or reconnaissance stages of your exploration, nickel laterite deposits are more or less located in areas with mafic and ultramafic host rock. So and they have relatively high density compared to other types of rocks. So we can use gravity to look for these host rocks. And then for magnetics, uh, the alterations involved in nickel laterite deposits, particularly the acid leaching, destroys your magnetites. So we can expect low magnetic signatures in the actual laterite deposits. And then for resistivity, all right, you also have high concentrations of sulfides in nickel laterite, and that can register as high resistivity. Okay, so this ends the lecture for the applications of geophysics. More or less, I have also introduced the geophysical methods. So for the next lecture, we will be discussing the basic concepts of geophysics and then we move on to the specific geophysical methods. Right? Thanks for listening.